26,000 light-years from where you are sitting right now, something enormous waits at the very center of our galaxy. For decades, we treated it as a quiet, distant textbook fact, a dead weight, a gravitational anchor humming in the dark. Then the James Webb Space Telescope pointed its instruments at that exact spot. What it saw was not the stable, sleeping giant we had comforted ourselves with for years. It was something flickering, flaring, and moving in patterns that do not match any prediction. Something unpredictable, something active, something that was never truly asleep. And the more Webb clarified the picture, the less settled the center of the Milky Way appeared. This is the story of how our own galactic heart became much harder to look at. If you find yourself drawn to stories like this, the kind of science that looks straight into the places we would rather not think about, take a moment to like the video and subscribe. It genuinely helps more than you might think, and it lets me keep exploring these strange corners of the cosmos with you. Are you nice and comfortable? Now, let's begin. For most of human history, when people looked up at the band of soft light we call the Milky Way, they were looking directly at the heart of our galaxy without knowing it. That pale river of stars arcing across a dark summer sky is not just a pretty smear. It is the edge-on view of the flattened disk we live inside, and the brightest, densest part of that river, the part that swells toward the constellation Sagittarius, is pointing straight at the center. Every clear night, if you are standing somewhere far from city lights, you are looking in the direction of a place roughly 26,000 light-years away. A place you cannot see. A place that has been hiding behind layers of dust and gas so thick that for centuries no telescope could pierce them. A place that, we now know, contains something very strange. That something is Sagittarius A star, pronounced Sagittarius A star, written with a small asterisk in the scientific literature. It is a supermassive black hole, with a mass of roughly 4 million times the mass of our Sun. It sits at the gravitational pivot of the Milky Way. Every star in the galaxy, including ours, traces a slow, enormous orbit around it. Our solar system is doing it right now. It takes us about 230 million years to complete a single lap. Dinosaurs were still alive the last time we were at this point in the orbit. And yet, for almost all of that history of careful skywatching, Sagittarius A star was completely invisible to us. Not faint, not hard to resolve. Invisible. You could point the finest optical telescope ever built directly at the galactic center and see nothing of it, because the line of sight is blocked by vast clouds of interstellar dust that absorb visible light almost completely. If you took all of the dust between us and the galactic center and spread it evenly along that path, you would still have enough obscuration to dim the light behind it by a factor of roughly 1 trillion. That is not a typo. 1 trillion. The heart of our own galaxy has been sealed off from our eyes by a curtain of cold matter thicker than anything our visual imagination was built to handle. Which is why, for most of the 20th century, we simply did not know what was there. The first clue came not from optical astronomy at all, but from radio. In 1933, a young engineer at Bell Labs named Carl Jansky, working on a problem that had nothing to do with the center of the galaxy, noticed a persistent hiss in the radio receivers he was testing. He traced it, carefully and stubbornly, to a source that rose and set with the stars, not with the sun. The source was in the constellation Sagittarius. Jansky did not know it at the time, but he had become the first human being to detect radio emissions from the galactic center. He had accidentally invented radio astronomy, and he had also, without realizing it, made the very first detection of the region that would eventually become known as Sagittarius A star. For decades after that, radio astronomers pushed closer and closer to the source. They found that the radio noise was not coming from one place, but from a complicated structure that they eventually named Sagittarius A. Inside that structure, they identified an eastern half and a western half. And inside the eastern half, buried in the tangle of gas and radio emission, they found one small, intense, compact point, a point that behaved like no other radio source they had ever mapped. In 1974, astronomers Bruce Balick and Robert Brown identified that compact point and gave it the name we now use. They added the star symbol to distinguish it from the broader, messier Sagittarius A region around it. That little typographic mark, borrowed from atomic physics where it denotes an excited state, stuck. Sagittarius A star was now an object with a name. But a name is not an explanation. For years after its discovery, no one could say with certainty what Sagittarius A star actually was. It was compact. It was stationary against the background of more distant sources. It emitted radio waves. It did not do many of the dramatic things other compact objects in the galaxy did. There were arguments, sometimes sharp ones, about whether it was truly a supermassive black hole or something else, a dense cluster of dead stars, a strange fermionic ball of dark matter, some exotic object we had not yet categorized. The data simply was not good enough to force a conclusion. The dust curtain kept winning. What finally broke the case open was one of the most patient pieces of observational astronomy ever attempted. Starting in the 1990s, two independent teams of astronomers decided that they would stare at the galactic center night after night, year after year, and track the motion of individual stars that happened to be orbiting the thing at its center. One team, led by Andrea Ghez, used the Keck telescopes on Mauna Kea in Hawaii. The other, led by Reinhard Genzel, used the Very Large Telescope Array in Chile. Both teams were working in the near-infrared because infrared light penetrates dust far better than visible light does. In infrared, the 1 trillion factor of obscuration drops to something much more manageable. The curtain is still there, but you can see through it. What they found was remarkable. A handful of stars, very close to the galactic center, were moving fast. Not fast in the ordinary astronomical sense, fast in a way that demanded a new mental category. One star, in particular, called S2, was traced on a complete elliptical orbit that takes about 16 years to complete. At its closest approach, S2 reaches a speed of roughly 8,000 kilometers per second. That is more than 2.5% of the speed of light being reached by an ordinary star, just because of how tightly it is orbiting whatever sits at the focus of its ellipse. From the orbital parameters, the shape of the ellipse, the period, and the way the star accelerates and decelerates, the mass of that central object could be calculated directly using the same gravitational laws Newton wrote down in the 1600s and Einstein refined in 1915. The answer was approximately 4 million solar masses. Now, you have to pause on that number, because it is easy to let it wash past you. 4 million solar masses means 4 million times the mass of our Sun, packed into a region so small that S2, at its closest approach, was skimming past it at a distance of only about 120 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. So S2, at closest approach, was passing the central object at roughly 4 times the distance from our Sun to Neptune. Nothing else in the universe can be that massive and that small except a black hole. No star, no stellar cluster, no exotic dark matter configuration. The numbers simply did not leave room for any other interpretation. By the early 2010s, the case was closed. Sagittarius A star was a supermassive black hole. In 2020, Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics for that discovery, sharing it with Roger Penrose, whose theoretical work on the inevitability of black hole singularities had laid the groundwork decades earlier. The Nobel Committee cited them for the discovery of a supermassive, compact object at the center of our galaxy. It was one of the few times in recent history that the Nobel Prize had been awarded for watching something that no one could actually see, using the motion of things around it as proof that it was there. And for a while, that felt like the end of the story. The heart of our galaxy had a name, a mass, a location. It had been caught. It had been filed. The public, to the extent that the public thought about any of this, could tuck Sagittarius A star away into the same mental drawer as the Andromeda Galaxy or the Crab Nebula. A distant, named, understood thing. A piece of cosmic furniture. That mental picture, which I want to describe very carefully, is the picture this entire series is about to dismantle. Before we dismantle it, we should look at it squarely, because it is the picture most people still carry. It is probably the picture you carried into this video. In that picture, Sagittarius A star is a point. It is 26,000 light-years away. 26,000 light-years is a distance so vast that light itself, moving at 300,000 kilometers per second, takes 26,000 years to cross it. In that picture, Sagittarius A star is comfortably far. You can imagine it as a pin stuck in a map of the galaxy, holding the whole thing together, but not really doing anything. It has a mass, a radius, a basic physical description. It fits into a box. You can write it on a textbook page in 2 lines. Central supermassive black hole, 4 million solar masses. Distance, approximately 26,000 light-years. That is all you really need, the picture suggests. The mystery is the mass. Once you know the mass, you know the object. And then, in April of 2019, something happened that made the mental picture feel even more complete. The Event Horizon Telescope collaboration released the first ever image of a black hole. It was not Sagittarius A star, actually. It was Messier 87 star, the supermassive black hole at the center of the galaxy. Messier 87, a giant elliptical galaxy about 55 million light-years away. The image was a fuzzy, orange donut, a bright ring surrounding a central dark region. It looked, to many people, slightly blurry and slightly disappointing and utterly transformative all at the same time. A black hole had been photographed. The thing that was supposed to swallow light had been, in some sense, seen. 3 years later, in May of 2022, the Event Horizon Telescope collaboration released the image people had been waiting for. The image of Sagittarius A star itself. Another orange donut, slightly smaller in appearance, slightly messier, but unmistakable. Our black hole, our galactic center, photographed. The image ran on the front page of newspapers around the world. It appeared on magazine covers. It got turned into desktop wallpapers and t-shirt prints. For a brief moment, the center of the Milky Way became something people actively looked at, instead of something they vaguely knew existed. And here is the thing about that image, the thing that matters for our story. That image was a still. It was not a photograph in the ordinary sense. The Event Horizon Telescope is not a camera with a shutter. It is a globe-spanning array of radio dishes linked together through a technique called very long baseline interferometry, which effectively turns the entire Earth into one enormous virtual telescope. To produce the Sagittarius A star image, the collaboration had to combine data taken across multiple nights in 2017, perform years of computation, reconcile model after model, and ultimately average together a vast amount of information to produce a single representative frame. The donut you saw was not what Sagittarius A star looked like at any one moment. It was a statistical composite of what it looked like across hours of observation. Even within the collaboration, this was understood as a fundamental limitation. Sagittarius A star is small. That sounds strange to say about a 4 million solar mass object, but physically, the event horizon of Sagittarius A star is only about 24 million kilometers across. That is smaller than the orbit of Mercury. The gas swirling around it moves at a substantial fraction of the speed of light. The timescale for material to complete one orbit near the event horizon is on the order of minutes. In an hour of staring, Sagittarius A star goes through many complete cycles of brightness variation. It flickers, it shifts, it does not sit still long enough to be photographed cleanly. Every honest summary of the Event Horizon Telescope result included this caveat. The image is a time average of something that is not, in fact, static. The collaboration themselves were candid about how much harder Sagittarius A star was to image than M87 star, the black hole they had published first. The reason was not distance or dust, it was a time scale. M87 star is roughly 1,500 times more massive than Sagittarius A star. Because the size of a black hole scales directly with its mass, M87 star's event horizon is proportionally larger, and the orbital period of material near it is proportionally longer. Changes that play out over minutes around Sagittarius A star take days or weeks around M87 star. In practical terms, M87 star sat still long enough for the Earth-spanning array to collect a coherent snapshot. Sagittarius A star did not. It kept shifting underneath the observation. The team had to develop entirely new computational techniques to extract a stable representative image from data in which the source was changing faster than the array could complete its measurements. The final image was not a photograph in any traditional sense. It was a hard-won statistical reconstruction pulled from underneath a moving target. The technical achievement was extraordinary. But the difficulty itself was a message, one that was easy to miss behind the triumph of the orange donut. The center of our galaxy would not hold still. But that caveat did not travel well. It did not fit easily onto a magazine cover. What was traveled was the image, the donut, the impression of a finished object, a cosmic portrait. And for most people who saw it, that was the moment Sagittarius A star graduated from an abstract gravitational pin to a visible thing, and with that graduation came the unspoken assumption that the work was done. We had found it. We had photographed it. Next question. This is the mental picture I want you to hold in your mind as we go forward. It is not a wrong picture. It is not a lie. Every piece of it is scientifically accurate. The mass is right. The distance is right. The image, within its stated limitations, is right. The Nobel Prize was deserved. The work was real. But the picture is incomplete in a specific way, and the incompleteness matters because what James Webb has added since is not a correction to any of these facts. It is a dimension the earlier facts did not contain. That missing dimension is time. Let me try to explain what I mean. Every observation I have described so far, the decades of stellar orbit tracking, the radio pinpointing of the source, the Nobel Prize-winning mass determination, the Event Horizon Telescope donut, all of them either treat Sagittarius A star as a static object, or they treat its variability as noise to be averaged away in order to recover the static signal underneath. The science was aimed at answering the question, what is this thing? Is it a black hole? How massive is it? What does it look like? Those questions, when you really inspect them, are questions about an object at rest. They assume that the right description of Sagittarius A star is the description you get when you stop time and ask, what is sitting there? But Sagittarius A star is not sitting there. It is doing things. Even when it is quiet, it is not quiet in any human sense. Material is continually falling toward it. Magnetic fields are twisting through the accretion environment. Plasma is being accelerated to relativistic speeds. The region around the event horizon is one of the most extreme physical environments in the known universe, and it is extreme all the time. The stillness of the textbook description, the stillness of the press release image, is not a property of the object. It is a property of how we chose to describe it. And for a long time, there was no real alternative. To see variability in Sagittarius A star with high fidelity, you need a telescope that can cut through the dust, resolve the region around the black hole with reasonable precision, and stare at it for long enough to watch behavior unfold. Ground-based infrared telescopes like Keck and the Very Large Telescope had been doing this for years, and they had seen flickering, they had seen flares. The presence of variability was not news. What had been missing was the kind of systematic, long-duration, high-sensitivity monitoring that would turn that variability from a curiosity into a data set. Ground-based observations are limited by atmospheric turbulence, by weather, by the rotation of the Earth. You cannot stare at a single point in the sky continuously from the ground. The Earth gets in the way. To appreciate what Webb changed, you have to understand what the ground-based record actually looked like. For roughly 2 decades before Webb's Galactic Center campaign, the Keck Observatory and the Very Large Telescope had been observing Sagittarius A star in the near-infrared. Both facilities used adaptive optics, a technology that measures atmospheric turbulence in real time and adjusts the shape of the telescope mirror hundreds of times per second to partially cancel out the blurring. The results were extraordinary by ground-based standards. Those teams could resolve individual stars within fractions of a light year of the black hole. They could track orbits. They could detect flares when they happened. But the data they collected had a texture that is important to understand. A ground-based observing run typically lasted a few hours per night, weather permitting. Between exposures, the atmosphere would shift, sometimes slightly, sometimes drastically. Clouds would roll through. The seeing would degrade and recover. Humidity would spike and force the dome to close. And the Earth, of course, would rotate, swinging the galactic center below the horizon at a fixed hour determined by the season and the observatory's latitude. From Mauna Kea, the galactic center is accessible for perhaps 6 hours on a good summer night. From Paranal in Chile, slightly longer. But neither site could provide continuous coverage. The result was a data set that looked less like a movie and more like a slideshow with missing frames. You would catch a flare in progress, but miss its onset. Or you would see the brightness rising at the end of one night and then lose the target below the horizon before you could watch it peak. Or you would come back the next night and find the brightness already settled, with no way of knowing whether it had stayed elevated for 20 minutes or 12 hours after you stopped watching. This was not a hypothetical problem. One of the brightest infrared flares ever recorded from Sagittarius A star was detected by Reinhard Genzel's team at the Very Large Telescope in 2003. When they picked it up, it was already bright. The onset had been missed. They watched it decline, but the full duration and the true peak luminosity were never captured. The most dramatic event they had ever seen from the galactic center arrived with its beginning already gone and its total energy budget permanently unknown. That single episode illustrated the fundamental limitation better than any statistical argument could. The gaps were not the observer's fault. They were intrinsic to the limitations of working through an atmosphere from a rotating platform. Within those gaps, the default assumption was silence. If you caught a flare, you reported it. If you saw quiescent emission between flares, you reported that too. And the picture that emerged from 2 decades of this kind of observation was what you might call a highlight reel. Dramatic events separated by periods of apparent calm. The flares were real. The calm, in retrospect, was never confirmed. It was just the absence of data. The gaps were being interpreted as quiet because there was nothing else to interpret them as. This is the specific thing Webb eliminated. Not the gaps themselves, strictly speaking. Webb's observing schedule is still divided into discrete sessions. But within those sessions, the coverage is unbroken. No atmosphere, no weather, no rotation below a horizon. When Webb stares at Sagittarius A star for 8 hours, it collects 8 hours of continuous data. No frames are missing. No transitions are hidden. For the first time, the record is complete enough to answer the question that ground-based work never could. Is the space between the flares actually quiet, or were we just not watching closely enough? The answer, as we are about to see, was the latter. That is the moment James Webb entered the story. Webb is not a replacement for the Event Horizon Telescope. It does not resolve the event horizon directly. Its angular resolution at the wavelengths relevant to Sagittarius A star is not quite sharp enough for that. What Webb does have is 3 things the ground-based infrared work never had in combination. First, it sits in space, above the atmosphere, with an uninterrupted view. Second, its infrared sensitivity is dramatically better than anything that came before. Third, it can be pointed at a single target for continuous multi-hour blocks of time, producing essentially unbroken records of how something changes. For an object whose most interesting behavior plays out over minutes to hours, that combination is transformative. When Webb was turned towards Sagittarius A star, what it delivered was not a new portrait, it was a time series. It was not the answer to the question, what does the center of our galaxy look like? It was the beginning of an answer to a different question, a much harder one. What does the center of our galaxy do? And this is the threshold I want to leave you at before we cross into the Webb data itself in the next part. Because you should understand that everything up to this point, from Carl Jansky hearing his radio hiss in 1933, through the decades of stellar orbit tracking, through the Nobel Prize, through the Event Horizon Telescope image, has been a story about pinning Sagittarius A star down, locating it, weighing it, confirming its basic nature. That story largely succeeded. We know it is there. We know what it is. We know, to within reasonable scientific tolerance, how massive and how distant it is. What that story did not do, what it could not do, was ask the follow-up question that has always been waiting underneath. If this thing is real, and this close, and this active, what is it actually doing, minute by minute, hour by hour, year by year? That question requires a different kind of instrument and a different kind of patience, and a willingness to stop treating Sagittarius A star as a noun and start treating it as a verb. In 2023, a team led by Farhad Yousefzadeh at Northwestern University began doing exactly that. They pointed the James Webb Space Telescope at Sagittarius A star and watched it for hours at a time across multiple observing sessions spread over nearly a year. They did not expect to see nothing. They expected to see activity. Everyone who had worked on this object had seen glimpses of activity in ground-based data for decades. What they got instead was more than activity. It was something that, when the paper finally came out, made the scientists describe the behavior using words that had not been used for Sagittarius A star in any previous era: bubbling, flickering, continuous, no underlying rhythm, no quiet baseline, not a sleeping giant, occasionally twitching, a restless environment, permanently alight, punctuated by sudden eruptions that nobody could predict. The donut, it turned out, was not a donut. The donut was a long exposure of a candle flame. And when you slow the exposure down to catch the flame itself, the whole shape of what you thought you were looking at begins to move. That is where the comfortable distance ends. That is where the mental picture starts to crack. You thought you knew what was at the center of our galaxy. You thought it was a 4 million solar mass pin, stuck in a map, holding things together, photographed and filed. You were not wrong about the mass. You were not wrong about the distance. You were wrong about the stillness. And once the stillness goes, everything else about how you have been quietly imagining Sagittarius A star, its distance, its passivity, its separation from the world you live in, starts to look different too. What Webb actually saw, when it stared directly at the heart of the Milky Way for long enough to watch that heart move, is what comes next. To understand what James Webb did when it looked at Sagittarius A star, you first have to understand what Webb is, and more importantly, what it can do that nothing before it could. Because the word telescope is doing a lot of quiet work here, when most people hear telescope, they picture a tube you put your eye against, or at most a large observatory dome on a mountaintop. Webb is not that. Webb is a 6.5-meter wide gold-coated mirror unfolded like origami in deep space, floating 1.5 million kilometers from Earth, permanently shaded from the sun by a tennis court-sized heat shield, cooled to temperatures so cold that its instruments can detect heat signatures from objects so faint and so distant that they would be completely lost against the background warmth of anything less insulated. That cooling is the whole point. Webb is an infrared telescope. Infrared light is, at its simplest, heat. Everything warm glows in infrared, including the telescope itself, which is why Webb has to be kept so cold. And crucially, infrared light passes through interstellar dust in a way visible light cannot. That 1 trillion factor of dimming that we talked about earlier, the curtain that has hidden the galactic center from every optical telescope ever built, becomes almost transparent at the wavelengths Webb is designed to see. In infrared, the curtain thins out. The dust stops mattering. You can look straight through to what lies behind it. This is why Webb is the right tool for Sagittarius A star. Every earlier era of galactic center astronomy had to fight the dust. Radio astronomy won by choosing wavelengths that slipped past it. Ground-based infrared work, like Keck and the Very Large Telescope, won by choosing wavelengths that punched through it, at the cost of atmospheric interference. Webb combines the dust-piercing capability of infrared with the stability of a space-based platform and a mirror larger than anything previously sent above the atmosphere. It does not have to fight the dust. It does not have to fight the atmosphere. It does not have to wait for a clear night. It just looks, continuously, for as long as the observing schedule allows. Which brings us to the actual observations. In April and September of 2023, and again in April of 2024, a research team led by Farhad Yousefzadeh of Northwestern University used the near-infrared camera on board Webb to stare at Sagittarius A star. The total observing time across those campaigns came to roughly 48 hours, split across multiple sessions of 6 to 12 hours each. That may not sound like much. In the context of ground-based galactic center work, where a single night of useful data might involve a few usable hours between clouds and bad seeing, it is a staggering amount. It is the difference between watching a few isolated still frames and watching something that begins to resemble a movie. What they saw, and what they published in a paper in the astrophysical journal Letters in February of 2025, was not the Sagittarius A star of the textbooks. It was not a point of steady brightness with occasional flares. It was something Yousefzadeh described, in the plainest language a working astrophysicist ever allows himself, as flickering all the time. Let me say that again, because I want the weight of it to land. Flickering all the time. not flickering during flares, not flickering when disturbed, flickering all the time. At every moment, in every observation, across every session, the brightness of Sagittarius A star in the infrared was varying. The baseline was not a baseline. There was no quiet state to return to. The object was in continuous motion, brightening and dimming and brightening again, on timescales of seconds and minutes, with no apparent rhythm and no apparent rest. Superimposed on that constant low-level flickering were larger events, flares. Brighter, longer eruptions in which the luminosity of Sagittarius A star would jump by a substantial factor for anywhere from minutes to roughly an hour, before settling back down into the flickering baseline and waiting for the next one. Across the 48 hours of Webb monitoring, the team identified 5 or 6 of these larger flares, depending on how strictly you define the threshold. That means a major flare, on average, roughly once every 8 to 10 hours, and between the big flares, the smaller subflares and flickers were essentially continuous. Now, the existence of flares at Sagittarius A star was not a surprise. Ground-based infrared work had been seeing flares there for more than 20 years. The Chandra X-ray Observatory had seen them in X-rays. The ALMA array had seen them in millimeter waves. Flares were known. Flares were expected. What Webb did was not discover that Sagittarius A star flares. What Webb did was watch it for long enough, and carefully enough, to see that the flaring is not the interesting story. The interesting story is what happens between the flares, which turns out to be a continuous, restless activity that nobody had been able to resolve before. And here is the detail that made the scientific community stop and reread the paper. The team tried, as any team would, to find patterns in the flickering. Is there a preferred timescale? Is there a characteristic period? Does the flickering repeat? Does it cluster? They applied the standard statistical tools. They looked for periodicities. They looked for correlations between flare timing and flicker amplitude. They looked for any underlying clock. They found nothing. No periodicity. No characteristic timescale in the classic sense. No repeatable pattern. The best statistical description of the behavior was what physicists call colored noise, a kind of mathematical chaos that has structure in a technical sense, but does not predict anything you could bet on. If you watch Sagittarius A star for an hour, you could not tell anyone with any confidence what it would be doing in the next hour. You could only say that it would, almost certainly, still be flickering, and that a flare could come at any moment, or not come at all. This is a very different object from the one in the textbook. Textbook Sagittarius A star is a mass and a position. Webb, Sagittarius A star, is a process that never stops, a process that cannot be reduced to a number. To understand why this matters physically, and not just dramatically, you have to understand what is happening in the space immediately around the event horizon. Sagittarius A star is what astrophysicists call a low-luminosity supermassive black hole. Compared to the violent quasars at the centers of distant galaxies, it is feeding very slowly. The rate at which it is accreting matter is millions of times below the theoretical maximum for its mass. In the scale of cosmic appetites, it is picking at its food. This is one of the reasons early astronomers could not easily identify it as a black hole. A ravenous black hole lights up the region around it like a lighthouse. A slow, quiet black hole does not. But slow is not the same as off. Even at its reduced feeding rate, Sagittarius A star is surrounded by a thin, hot, turbulent atmosphere of ionized gas, spiraling inward along complicated magnetic field lines. Some of that gas is infalling from farther out. Some of it is the shed outer layers of stars that have passed too close. Some of it is matter that has been orbiting the region for a very long time, slowly losing energy and working its way in. The flow is not smooth. It is not a clean disk the way you see in movie depictions of black holes. It is a messy, clumpy, magnetically threaded environment in which plasma is being accelerated, compressed, reconnected, and reheated on a continuous basis. Every time two magnetic field lines of opposite polarity get pushed together in that environment, they can reconnect, releasing energy in a sudden burst. The same process drives solar flares on our own sun at vastly smaller scales. In the accretion environment around Sagittarius A star, these reconnection events happen continuously because the plasma is continuously churning. Each reconnection heats a small region of gas, accelerates electrons to relativistic speeds, and produces a burst of light across the electromagnetic spectrum. The result, as seen from Earth, is flickering. Small reconnection events produce small flickers. Large reconnection events, where a major structural rearrangement of the magnetic field occurs or a particularly dense clump of gas falls in, produce flares. What Webb has added to this picture is the continuity. Before Webb, you could see the flares, and you could infer that something less dramatic must be happening between them. After Webb, you can see the something less dramatic. And the something less dramatic turns out to be itself something, a perpetual low-grade storm threaded through the accretion flow, never quieting, never resolving into a steady state. This changes how you have to think about Sagittarius A star. A static black hole is a thing. A perpetually storming black hole is an environment. And environments, unlike things, have to be characterized in terms of their dynamics, not their parameters. You can write down the mass of Sagittarius A star in one line. You cannot write down, in any finite number of lines, what it will look like at any given moment, because that depends on the full history of the magnetic and plasma configuration around it, and that configuration is chaotic in the technical sense. Small perturbations grow into large differences. The system has no memory of where it started. It is not reducible. The absence of periodicity deserves more attention because it is not merely an observation, it is the failure of a prediction. And failed predictions, in science, are where the real information lives. Before Webb's monitoring campaign, there were good theoretical reasons to expect that Sagittarius A star's variability might contain a characteristic timescale. The strongest candidate was the orbital period of gas near the innermost stable circular orbit, the closest radius at which material can orbit a black hole without spiraling inward. For a black hole of Sagittarius A star's mass, that orbital period is roughly 30 minutes, depending on the black hole's spin, which we do not yet know precisely. If gas orbiting at that radius were producing the dominant emission, you would expect the brightness to modulate on roughly that timescale. A bright blob of gas circling the black hole every half hour would produce a periodic signal that any time series analysis would pick up. There was another candidate timescale too, the light crossing time of the event horizon, which for Sagittarius A star is on the order of a minute. If the flares were being produced by coherent disturbances propagating across the emission region, the flare duration should cluster around multiples of that crossing time. You would not get a clean periodic signal, but you would get a preferred timescale embedded in the noise. And there was a third expectation rooted in what had already been observed in other accreting black holes. In X-ray binary systems, stellar mass black holes accreting from companion stars often show quasi-periodic oscillations, rhythmic brightness variations that indicate a preferred frequency in the accretion flow. If the physics scales with mass, as many accretion models predict, Sagittarius A star should show analogous oscillations at correspondingly longer periods. The search for these quasi-periodic signals in the galactic center had been ongoing for years, with tantalizing hints in some datasets and null results in others. Webb was expected to settle the question, because its combination of sensitivity and continuity made it the ideal instrument for detecting weak periodic signals buried in noise. If the periodicity was there, Webb would find it. It did not find it. Not at 30 minutes, not at 60 minutes, not at any timescale the team tested. The variability is broad spectrum. It contains power at all timescales within the observed range, declining roughly as a power law, with no peak, no bump, no preferred frequency rising above the continuum. The process driving the emission is not organized around any single timescale. It is distributed. It is turbulent in the technical sense. The accretion flow near Sagittarius A star's event horizon appears to be a fully developed turbulent cascade, where energy is injected at larger scales and transferred to smaller scales through a process that has no preferred stopping point. This is a real constraint on the physics. It rules out models in which the emission is dominated by a single hot spot orbiting at the innermost stable circular orbit. It rules out models in which a coherent disk oscillation drives the variability. What it favors is a picture in which the emission comes from a disordered tangle of magnetic reconnection events distributed throughout the accretion flow, firing off at all sizes and all timescales in a way that no single physical clock controls. The center of our galaxy is not pulsing, it is crackling, and the crackle has no rhythm. There is another layer to the Webb observations that I want to emphasize, because it is subtle and because it matters for the bigger picture. Webb did not just see the flickering and the flares. It saw something about the flares themselves that had not been cleanly established before. The brightness of each flare is slightly different at two infrared wavelengths Webb observes simultaneously. The near-infrared camera can capture light at two slightly different infrared colors in the same exposure, essentially taking two movies of Sagittarius A star at the same time in two different shades of infrared. When the team compared the two movies, they found that the flares do not peak at exactly the same moment in both colors. There is a small but measurable delay. The shorter wavelength light peaks first. The longer wavelength light follows, by a few seconds to tens of seconds. This is not a random curiosity, it is a fingerprint. The delay between the two colors matches what you would expect if the flares are produced by a population of high-energy electrons that are cooling as they radiate. The electrons start out with very high energies, emitting at the shorter wavelengths, and as they lose energy through radiation and other processes, their emission shifts to longer wavelengths. The color delay is the signature of that cooling. It tells the observers directly that they are watching energetic electrons being accelerated somewhere in the accretion environment and then losing energy on a time scale of seconds. That is an extraordinary piece of information. It pins down a physical process at the event horizon scale, not through inference, not through modeling alone, but through direct observational consequence. It also confirms that the mechanism driving at least the short-duration flares is something fast, something operating on second timescales, something like magnetic reconnection, where energy is released suddenly and electrons are accelerated in a brief burst. The longer flares, the ones that last for tens of minutes or more, may be driven by a different process, possibly the infall of compressed clumps of matter near the event horizon. The data cannot yet distinguish those scenarios cleanly, but the fingerprint is there. So now, stack up what Webb has actually shown us. 1. Sagittarius A star is never quiet. The flickering is continuous across every observation. 2. The flares on top of the flickering are more frequent than expected, with major events occurring on the order of once every several hours rather than once every day or two. 3. The flares carry a physical fingerprint the color delay, that confirms energetic particle acceleration is happening on second timescales in the environment around the black hole. 4. None of this has a detectable periodicity or pattern. It cannot be predicted. It can only be described statistically. Place all of that against the mental picture we started with. The mental picture was a still donut, a photographed, filed, finished object, a piece of cosmic furniture at a comfortable distance. What Webb has handed back is something else. Not a different object, the same object, but seen with enough time resolution to reveal that it was never actually still. The stillness was a property of our observations, not of the thing itself. And this is where the Webb result starts to do something to your sense of the galactic center that I want to be very precise about. It does not make Sagittarius A star dangerous. It does not make it closer in any physical sense. It does not change the mass. It does not change the distance. 26,000 light-years is still 26,000 light-years. The flares are not going to reach Earth. The flickering is not a sign of escalation. None of this is apocalyptic. Anyone telling you that the galactic center is suddenly threatening is not reading the data. What Webb does is more subtle and more conceptually unsettling. It removes the stillness. And the stillness was doing a lot of emotional work that most of us never noticed. As long as Sagittarius A star was a static pin at a fixed distance, it could be treated as inert. Massive, yes. Nearby on a cosmic scale, yes. But essentially over, finished. A thing that had happened. A thing we had measured and moved past. Webb's time series makes that treatment no longer honest. The thing at the center of our galaxy is not over, it is ongoing. Right now, as you are hearing this sentence, Sagittarius A star is flickering. 26,000 years ago, when the light that arrives today was first emitted, a flare may have gone off that our descendants, or our successors, will see arriving at some unpredictable moment. Between the flares, the flickering has never stopped. There is no moment in recorded history when the heart of the Milky Way was still. There probably never has been such a moment. The stillness was never a property of the object. It was a property of our ignorance. And once that is clear, the next question arrives almost automatically. Why is it doing this? What is feeding this continuous activity? If Sagittarius A star is accreting matter at a rate millions of times below its theoretical maximum, where is even that slow trickle of matter coming from? What is happening in the environment immediately around the black hole that keeps the accretion flow churning this violently at every moment? The preliminary answer, based on the Webb data combined with other observations, points to something uncomfortable. The environment around Sagittarius A star is not a smooth bath of gas. It is a region of extreme turbulence, where magnetic fields are being twisted and reconnected continuously, where the plasma is inhomogeneous on every scale that can be probed, where clumps of material are falling in on trajectories that cannot be predicted. The flickering is not noise on top of an underlying quiet flow. The flickering is the flow. There is no quiet underlying state. The turbulence goes all the way down. That is a very different physical picture from the one most people carry. In the casual mental image, a black hole sits at the center of a smooth, organized disk of infalling material, like a drain at the bottom of a bathtub. Matter spirals in along orderly paths, heats up, emits light, and eventually crosses the event horizon. Webb's data is not consistent with that picture at the small scales. At the small scales, near the event horizon of Sagittarius A star, there is no bathtub drain. There is something more like a permanent thunderstorm, with lightning going off continuously and larger strikes happening several times a day, all of it crammed into a region smaller than the orbit of Mercury, at the gravitational pivot of a galaxy containing hundreds of billions of stars. There is one more thing worth saying about the Webb observations before we move on. because it sets up what comes next. Webb did not see Sagittarius A star in isolation. In the same field of view, in the same data, it captured the immediate environment around the black hole. The gas, the dust, the neighboring stars, the compact dusty objects known as G objects, the streamers, the clumps, the entire neighborhood in which Sagittarius A star is embedded. And that neighborhood, which we have barely been able to resolve before, is not a calm backdrop against which the black hole flickers. It is itself an active, structured, dynamic place. The flares are not happening in a vacuum. They are happening inside a tangle, which means that to really understand what Webb has revealed, you cannot stop at the event horizon. You have to zoom out. You have to ask what the region around Sagittarius A star actually looks like when you clear away the dust and watch it work. Because the activity at the event horizon is not self-generated. Something is feeding it. Something is supplying the gas, dropping the clumps, twisting the fields, and that something is a neighborhood far stranger and far more crowded than the textbook allows. For years, we treated the galactic center as a single-named object with a single name on a map. Webb, by accident as much as by design, has begun to show that the name was covering a whole landscape. The black hole is the most famous resident. It is not the only resident, and the longer you stare at what surrounds it, the harder it becomes to maintain the idea that the center of the Milky Way is a simple place. That is where we turn next. Zoom out. Not far, not to the scale of the galaxy, just a few light years. Take the black hole you have now been staring at for this long, the flickering, flaring, perpetually unsettled mass at the center of everything, and let the view widen until you can see not just the event horizon region, but the space around it, the immediate neighborhood. The first few light years in every direction from the gravitational center of the Milky Way. What you find there is not empty. It is not even sparse. The galactic center is one of the most crowded, most energetic, and most physically extreme environments in the entire galaxy, and the more Webb reveals about it, the harder it becomes to maintain the idea that Sagittarius A star is a solitary object sitting in a void. It is not solitary. It is embedded in a tangle of stars, gas, dust, magnetic structures, and objects that do not fit cleanly into any existing category. And that tangle is not passive. It is interacting with the black hole on every time scale from minutes to millions of years. The flares and flickers we talked about earlier do not come from nowhere. They come from here. Start with the stars. In the innermost fraction of a light year around Sagittarius A star, there is a population of stars that should not, by every normal expectation of stellar dynamics, be where they are. They are called the S stars. We already met S2 earlier, the star whose 16-year orbit clinched the Nobel Prize. But S2 is not alone. It is part of a cluster of several dozen stars, all orbiting Sagittarius A star on tight, fast, elliptical paths, all of them tracing the same invisible center of mass. Some of them are closer than S2, some are faster. One star, known as S4714, has been clocked at speeds exceeding 24,000 kilometers per second during its closest approach. That is roughly 8% of the speed of light. An ordinary star, made of hydrogen and helium, the same basic stuff as our Sun, moving at 8% of the speed of light because of the gravitational influence of the thing it orbits. Think about what that means physically. At those speeds, relativistic effects are no longer corrections in a textbook. They are measurable. Time dilation, gravitational redshift. The precession of the orbit predicted by general relativity, the same effect that was first observed in Mercury's orbit in the 19th century, becomes large enough to see directly in the S-star orbits over the span of a few years. These stars are living laboratories for extreme gravity, And they are sitting right next to us, cosmically speaking, at the center of our own galaxy. But here is the puzzle that has bothered astrophysicists for decades. How did they get there? Stars do not form easily near a supermassive black hole. The tidal forces are immense. The gravitational shear in the region around Sagittarius A star is powerful enough to rip apart the molecular clouds that stars normally condense out of. Any cloud of gas that wanders too close should be stretched and disrupted long before it can collapse under its own gravity and ignite nuclear fusion. Yet, the S stars are there. They are young, many of them, only a few million years old, spectral Class B stars with high masses and short lifetimes. They did not drift in from far away over billions of years. They arrived or formed recently, by galactic standards. One leading hypothesis suggests they were delivered. A dense cluster of stars may have spiraled inward from farther out in the galaxy through a process called dynamical friction, where the gravitational drag of surrounding matter slowed it down and caused it to sink toward the center. When the cluster got close enough, the tidal forces of Sagittarius A star tore it apart, scattering its members into the orbits we observe now. Another hypothesis proposes that a massive disk of gas, dense enough to resist tidal disruption, once existed close to the black hole, and stars formed directly within that disk. Both ideas have support. Neither is fully settled. The point is that even the presence of stars in this region tells a story of violence and disruption. Nothing about the galactic center is simply sitting where it formed. Everything has been processed, rearranged, torn apart, or delivered by mechanisms that involve enormous energies. The mystery of the S stars is worth pausing on, because it is not just an unsolved puzzle. It is a puzzle whose continued unsolvedness tells us something about the galactic center as an environment. The basic problem is this: the stars closest to Sagittarius A star are spectral Class B stars. They are hot, luminous, and massive, typically 10 to 15 times the mass of our Sun. Stars like these burn through their nuclear fuel relatively quickly and live for only about 10 to 50 million years. They are young. They must have formed recently. But the environment they occupy is almost uniquely hostile to star formation. Star formation, everywhere we have observed it in the galaxy, requires roughly the same starting conditions. A cloud of cold molecular gas has to reach a density where its own gravity overwhelms the pressure pushing outward, and it collapses. The collapse produces a protostellar core. The core accretes more material from the surrounding cloud. Eventually, the center gets hot and dense enough to ignite hydrogen fusion, and a star is born. The whole process requires the cloud to hold together long enough for gravity to win. Near Sagittarius A star, gravity does not cooperate. The tidal force from the black hole, the difference in gravitational pull between the near side and the far side of any extended object, is enormous. A molecular cloud drifting into the central parsec would be stretched along its orbital direction and compressed perpendicular to it. The stretching overwhelms the cloud's self-gravity at distances well beyond where the S stars orbit. By every standard calculation, any cloud that wandered close enough to form stars where the S stars are would have been torn into thin filaments long before it could collapse. So the stars should not be there, and yet they are. The two leading scenarios each carry their own implications. The cluster in spiral model, proposed in various forms by several groups, imagines that the S stars were born in a normal star-forming region farther from the center, perhaps tens of light-years out, where tidal forces are manageable. They formed inside a dense, massive star cluster that then spiraled inward through dynamical friction, the gravitational drag exerted by the background of stars and dark matter. When the cluster reached the tidal disruption radius, the black hole's gravity pulled it apart and scattered its members into the orbits we see today. This is plausible. The timescales work out. But it requires the original cluster to have been very massive and very compact, and it requires the inspiral to have happened recently enough that the young stars have not yet burned out. The fine-tuning is uncomfortable. The disk formation model imagines something different. At some point in the past, a large mass of gas fell into the central region and settled into a dense, thin disk orbiting the black hole. If the disk was massive enough and dense enough, it could have resisted tidal disruption long enough for gravitational instabilities within the disk to fragment the gas and form stars in place. Some of the observed S-star orbits do lie in a rough common plane, which supports this idea. But other S-star orbits are randomly oriented, which undermines it. And the disk itself would have had to be an unusual object, far denser than any protostellar disk observed elsewhere. What both scenarios share is violence. Neither allows the S-stars to have formed gently in the kind of serene stellar nursery you see in Hubble images of nearby molecular clouds. The stars, closest to the heart of the Milky Way, arrived there through disruption, through dynamical chaos, through processes that leave wreckage. Their very presence is evidence that the galactic center does not merely contain a black hole. It processes everything that enters it. And the S-stars are the ones we can track. Deeper in, closer to the black hole, there are objects that are stranger still. They are called G objects, and they represent one of the most genuinely puzzling populations in galactic center astronomy. The first one, G1, was identified in the early 2000s. The second, G2, was discovered around 2011 and became briefly famous because its orbit was predicted to bring it extremely close to Sagittarius A star in 2014. Astronomers watched with fascination, expecting to see G2 torn apart by tidal forces, producing a fireworks display of infalling gas that might light up the accretion environment in a way never before observed. That is not what happened. G2 passed through its closest approach and survived. It was stretched. Its shape was distorted. It got elongated along its orbit like a piece of cosmic taffy being pulled. But it did not disintegrate. It held together, which told astronomers something important and unsettling. G2 was not a simple gas cloud. If it were just a cloud, the tidal forces at that distance from Sagittarius A star would have shredded it. It must have a denser object inside it, something massive enough to hold the surrounding gas and dust together gravitationally, even as the black hole tried to tear it apart. The story of G2's close approach deserves a fuller telling, because it was one of the most anticipated astronomical events of the decade, and its outcome taught the community something important about assumptions. G2 was discovered around 2011 by a team led by Stefan Gillessen at the Max Planck Institute for Extraterrestrial Physics. Its orbit was calculated. The periapse, the point of closest approach to Sagittarius A star, was predicted for early 2014. The minimum distance would be roughly 25 light-hours from the black hole, well inside the tidal disruption radius for a simple gas cloud of G2's estimated size. If G2 was what it appeared to be, a diffuse cloud of ionized gas with no internal structure, it was going to be destroyed. The anticipation was intense. Observing proposals were written. Telescope time was allocated on Keck, on the Very Large Telescope, on Chandra, on radio arrays. Theorists published dozens of papers predicting what the disruption would look like. Some models forecast a dramatic brightening of Sagittarius A star as the shredded gas from G2 spiraled inward and hit the accretion flow. Others predicted a spectacular tidal tail stretching across the sky. A few more conservative models suggested the interaction might be modest, but even the conservative predictions expected visible structural changes in G2 itself. The event was, in public terms, described as the galactic center getting a meal. After years of watching Sagittarius A star sitting quietly, here at last was an opportunity to watch it feed. The expectation was not that it would become a quasar. Nobody expected that. but a detectable brightening, a flare, a visible distortion in the accretion environment that seemed almost certain. It did not happen. G2 reached periaps. It passed through closest approach. It was stretched. Infrared observations showed it elongating, its shape distorting under tidal stress. But it held together. It did not break apart. It rounded the black hole and began receding along the outgoing leg of its orbit, battered but intact. The anticipated fireworks never materialized. Sagittarius A star did not brighten. No new gas was delivered to the accretion flow in any detectable quantity. The anticlimax was, in a way, more informative than the spectacle would have been. It told astronomers that G2 was not a simple gas cloud. It had to contain something dense at its core, something whose gravity held the envelope together against the tidal forces that should have shredded a diffuse cloud. The survival of G2 pushed the community toward the stellar merger interpretation that now dominates the field. The non-event was the data. And the data said that the objects orbiting closest to Sagittarius A star are stranger, more resilient, and more internally complex than anyone had assumed. The current best guess is that G objects are the results of stellar mergers. Two stars in a binary system, orbiting each other while also orbiting Sagittarius A star, gradually spiral together under the influence of tidal interactions and merge into a single bloated object surrounded by a thick envelope of expelled gas and dust. The envelope makes them look fuzzy and extended. The merged star at the center gives them enough mass to resist tidal disruption. The whole package drifts on an orbit that brings it dangerously close to the black hole, where it gets stretched and heated, but not destroyed. Since G1 and G2, several more G objects have been identified. Webb's infrared sensitivity has made them easier to spot and easier to track. What is emerging from the data is not a handful of curiosities, but a population. There may be dozens of these objects in the innermost region of the galactic center. Each one is a small, self-contained drama of tidal interaction, a compact, dense core wrapped in a fragile shell of gas that is being slowly peeled away by the gravitational environment. Some of them will eventually lose their envelopes entirely. Some may eventually be disrupted. When they are, the gas they release will feed the accretion environment around Sagittarius A star, producing the kinds of flares and brightness variations that Webb has been watching. The G objects are, in a very real sense, the fuel supply of the flickering. Now, pull the view out a little further. Beyond the S stars and the G objects, but still within a few light years of the center, there is a structure that ground-based infrared telescopes have known about for decades, but never been able to map with the precision Webb provides. It is called the mini-spiral, or in technical terms, Sagittarius A West. And it is a set of ionized gas streamers that curve through the central cavity of the galactic center, like arms reaching inward from different directions. These are not spiral arms in the galactic sense. They are individual streams of hot gas, each with its own velocity and trajectory, falling toward the central region from the surrounding molecular material. The mini-spiral has at least three major components that astronomers have given prosaic names: the northern arm, the eastern arm, the western arc. Each one traces a different path through the gravitational potential of Sagittarius A star, and each one is being shaped by the combined influence of the black hole's gravity, the magnetic fields threading the region, and the radiation pressure from the dozens of hot young stars nearby. Webb has added fine detail to these structures, revealing substructure within the arms, knots of denser material, filaments that twist along magnetic field lines, and regions where the gas appears to be interacting with individual stars or G objects as it flows past them. The importance of the mini-spiral is not its beauty. though it is strikingly beautiful in infrared images. The importance is what it represents functionally. These streamers are the supply lines. They carry gas from the denser molecular material farther out toward the accretion environment near the black hole. Without them, Sagittarius A star would have very little to eat. The fact that they exist, and that they are structured and dynamic rather than smooth and uniform, means that the feeding of the black hole is not a continuous, gentle drizzle. It is episodic, lumpy, and dependent on the complicated geometry of how gas enters the central region. When a denser clump embedded in one of these streamers reaches the inner accretion zone, the result is a flare. When the flow is thinner, the result is the lower-level flickering. The mini-spiral is the context that makes sense of what Webb saw at the event horizon. Pull out further still. Surrounding the mini-spiral, at a distance of roughly 1.5 to 2 parsecs from the center, there is a thick, torus-shaped ring of colder, denser molecular gas called the circumnuclear disk. This is the reservoir. The circumnuclear disk contains several tens of thousands of solar masses worth of molecular material, orbiting the central region in a rough ring. It is the closest large body of dense gas to Sagittarius A star, and it is the source from which the mini-spiral streamers are drawn. The inner edge of the circumnuclear disk is being sculpted by the radiation and winds from the cluster of massive young stars that live near the black hole, and by the gravitational influence of the black hole itself. It is not a smooth donut. It is clumpy, turbulent, and threaded with filaments of warmer gas that extend inward toward the center. Webb has begun to resolve the fine structure of the circumnuclear disk's inner edge in a way that ground-based telescopes could not. What it sees is a boundary that is not clean. Gas is leaking inward through channels and gaps. Knots of material break off from the inner wall and begin their slow, spiraling journey toward the center. The boundary between the reservoir and the active region is porous. Material crosses it continuously, not in a flood, but in a steady, irregular seepage that keeps the whole system alive. Webb's contribution to mapping this inner environment goes beyond simply seeing what was already known at higher resolution. It has revealed structural details that were genuinely invisible before. One of the most striking results from the early Webb imaging of the galactic center is the detection of fine filamentary structures within the mini-spiral that had been completely unresolved in ground-based data. These filaments, narrow ridges of ionized gas only a few thousand astronomical units wide, trace paths that appear to follow local magnetic field lines rather than simple gravitational orbits. Their presence suggests that the flow of gas towards Sagittarius A star is not purely gravitational. It is magnetically channeled. Material does not simply fall inward along the shortest path. It is guided along magnetic highways that twist through the inner cavity in patterns determined by the interplay of the field geometry and the orbital dynamics of the gas. Webb has also resolved what appear to be bow shock structures around several of the massive young stars in the central cluster. These arcs of compressed gas form when the intense stellar winds from hot luminous stars collide with the ambient medium of the inner cavity. The shape and orientation of the bow shocks tell you how the wind is interacting with the surrounding gas, and by extension, how the surrounding gas is moving. Several of the bow shocks are oriented in directions that suggest the local gas flow is not aligned with what simple models of inflow would predict. The gas is moving sideways, or circulating, or being deflected by structures that the older maps could not see. There are also compact knots of warm dust that Webb has identified in the innermost region, previously invisible against the bright, diffuse background in lower resolution images. These knots are small, dense, and warm enough to glow brightly at Webb's operating wavelengths. Some appear to be associated with known sources. Others have no obvious counterpart in any other wavelength. They may be small clumps of material recently stripped from a passing star or G object. They may be fragments of a disrupted streamer. They may be something else entirely. Their identification is recent enough that the follow-up work is still in its early stages. What all of these new details share is a common theme. The innermost environment of the galactic center, the region within a few light-years of Sagittarius A star, is not a smooth bath of gas with a drain at the center. It is a structured, filamentary, magnetically threaded, shock-rich environment in which material moves along complicated paths determined by forces that cannot be reduced to gravity alone. Webb is showing that the plumbing of the galactic center is far more intricate than the old maps suggested, and the implications for how gas actually reaches the black hole, how flares are triggered, and why the accretion rate is so much lower than the available supply would allow, are only beginning to be worked out. And now, here is where the scale of the galactic center story starts to widen in a direction that most people have never considered. Everything I have described so far, the S stars, the G objects, the mini-spiral, the circumnuclear disk, fits within a box roughly 10 light-years across. That is the innermost sanctum. But the galactic center, as a physical environment, extends much further. The central molecular zone, a massive complex of dense molecular clouds stretching several hundred light-years across the inner galaxy, contains tens of millions of solar masses of gas and dust. It is the largest reservoir of dense molecular material in the entire Milky Way. It hosts regions of intense star formation and regions of strange quiescence. It contains filaments of ionized gas that stretch for tens of light-years in straight lines, aligned with the galactic center's magnetic field, structures that have no counterpart anywhere else in the galaxy. And, crucially, the central molecular zone carries scars, evidence of past activity from Sagittarius A star that far exceeds anything happening today. This is one of the most important things Webb has helped to clarify, and it connects back to the flickering in a way that makes the whole picture considerably more unsettling. Sagittarius A star today is dim. Compared to the supermassive black holes in active galaxies, it is millions of times quieter. Its current luminosity is a tiny fraction of what a black hole of its mass could theoretically produce. That dimness is part of why people were able to dismiss it as inert for so long. But the environment around it carries unmistakable signatures of past episodes in which it was not dim at all. The evidence comes from a direction most people would not expect, not from the black hole itself, but from its surroundings. Over the past 2 decades, X-ray observatories studying the central molecular zone have found something that, at first, seemed impossible. Cold, inert gas clouds lighting up in X-rays as if something had recently illuminated them from the inside. The phenomenon has a name. It is called a light echo. And what it reveals about the recent history of Sagittarius A star is one of the most startling results in galactic center science. The X-ray echo story is worth understanding in more detail because the evidence is surprisingly direct and the implications are large. The key observations came from the Chandra X-ray Observatory and from the European Space Agency's XMM Newton telescope, both of which have been monitoring the galactic center for more than 2 decades. What they found was that certain molecular clouds in the central molecular zone, dense clumps of cold gas that should be X-ray dark, were glowing, not steadily, not uniformly. Different clouds were brightening and fading at different times, in a pattern that moved outward from the position of Sagittarius A star like a ripple spreading across a pond. The physical mechanism is straightforward. When a powerful burst of X-ray photons is emitted by Sagittarius A star, those photons travel outward at the speed of light. When they strike a dense molecular cloud, some of the X-ray photons are absorbed by iron atoms in the cloud, which then re-emit the energy as fluorescent X-rays at a characteristic wavelength. The cloud lights up. It becomes an X-ray mirror, reflecting the original burst toward any observer who happens to be watching from a different angle. Because the clouds are at different distances from Sagittarius A star, they light up at different times. A cloud that is 50 light-years from the black hole will show the echo 50 years after a cloud that sits right next to the source. By mapping which clouds are glowing and measuring their distances, you can reconstruct when the original burst occurred. The cloud that has provided the most detailed constraints is called Sagittarius B2, a massive molecular complex located roughly 300 light-years in projection from Sagittarius A star. Its X-ray fluorescence has been tracked across multiple Chandra observing campaigns, and the brightness has been changing on timescales of years, consistent with the leading edge of a light echo sweeping through the cloud. The implied luminosity of the original flare is extraordinary. To produce the observed fluorescence at that distance, Sagittarius A star must have been emitting X-rays at a rate roughly 1,000,000 times higher than its current output. For a period of perhaps a few years, the black hole at the center of our galaxy was behaving less like the quiet object we see today and more like a low-luminosity active galactic nucleus. That was not millions of years ago. The light travel time calculations place the event within the last few hundred years. In human terms, while Galileo was pointing his first telescope at Jupiter, or while Newton was writing the Principia, the center of the galaxy was erupting in a way that would have been visible to X-ray telescopes if anyone had possessed them. We missed it, not because it was ancient, but because we were not ready to see it. The echo is all that remains, still rippling outward through the molecular clouds, carrying the memory of a flare that lit up the innermost galaxy on a timescale shorter than the age of most buildings you walk past on a city street. The Fermi Gamma-ray Space Telescope added another layer. In 2010, it revealed two enormous structures extending above and below the plane of the galaxy, centered on the galactic center. These structures, called the Fermi Bubbles, are lobes of high-energy emission reaching roughly 25,000 light-years in each direction, perpendicular to the galactic disk. Their edges are sharp. Their interiors glow in gamma rays. They are enormous. And their most likely origin is a period of intense activity from Sagittarius A star, probably millions of years ago, in which the black hole, or the star formation near it, drove a massive outflow of energy into the surrounding space. Between the Fermi bubbles and the X-ray light echoes, a picture emerges that is very different from the quiet anchor of the textbook. Sagittarius A star has not always been dim. It has gone through episodes of dramatically increased activity in the past, some of them geologically recent. It is not a retired engine, it is an intermittent one. The current, quiet state may be just that, a state, not a permanent condition. And this is where Webb's continuous monitoring data intersects with the broader galactic center picture in a way that produces genuine scientific unease. Because if you combine the two stories, the short timescale story of the flickering and flares that Webb sees minute by minute, and the long timescale story of the past outbursts written in the X-ray echoes and the Fermi bubbles, you get a picture of an object that is active on every timescale. It flickers on timescales of seconds. It flares on timescales of hours. It has undergone major luminosity increases on timescales of centuries. It has driven galaxy-scale energy injections on timescales of millions of years. At no timescale, from the shortest Webb can resolve to the longest, the geological record preserves, is Sagittarius A star truly quiet. That is the point. That is the sentence I want you to sit with. At no observed timescale is this object at rest. Webb has not seen the centuries-scale outbursts directly. It cannot. Those events are visible only through their echoes. But what Webb has done is fill in the short timescale end of the activity spectrum with enough detail to show that the pattern of intermittent activity extends all the way down. The same object that drove the Fermi Bubbles millions of years ago is also flickering right now, tonight, in infrared light that will reach us in 26,000 years. The same object that flared brightly enough a few centuries ago to light up molecular clouds across the central region is producing smaller flares every few hours, right now, as you hear this. The question this raises, and it is a question that the scientific community is actively working on, is whether there is a connection between the small-scale activity and the large-scale episodes. Are the flares Webb sees the low-grade rumblings of a system that occasionally erupts into something much more dramatic? Is the continuous flickering a sign that the accretion environment is always on the edge of a transition to a higher state? Or are the century-scale and million-year scale outbursts driven by entirely different mechanisms, like the sudden infall of a large gas cloud or a passing star, that have nothing to do with the everyday flicker? The honest answer is that we do not know. The data is too young. Webb has been watching Sagittarius A star for less than 2 years. The ground-based infrared record covers about 20 years. The X-ray echo record covers a few centuries. The Fermi bubble record covers millions of years. Connecting these timescales into a single coherent narrative of galactic center activity is one of the central open problems in the field. But the shape of the problem is now clearer than it has ever been, and the shape is uncomfortable, because what it suggests is that the object at the center of our galaxy does not have a default state. It does not have a normal. It has a range of behaviors, stretching from the barely detectable flicker at the low end to the galaxy reshaping outburst at the high end. And where it sits on that range at any given moment depends on what is falling into it, how the magnetic fields are configured, and whether a G object or a gas cloud or a star happens to be in the wrong place at the wrong time. There is one more piece of the neighborhood that I have to mention before we move on, because it is the piece that makes the whole picture feel most alive and most strange. Embedded in the innermost region, tangled up with the S stars and the G objects and the streamers and the magnetic filaments, there are structures that Webb has been resolving for the first time. Compact knots of warm dust. Narrow ridges of ionized gas that appear to trace the edges of shock fronts. Regions where the infrared brightness changes over months, suggesting that material is moving through them or being heated by events we have not identified. The inner few light years of the galactic center, seen in Webb's infrared vision, do not look like a quiet room with a heavy object in the middle. They look like the inside of a furnace. A furnace where the fire is distributed everywhere, where the fuel is being delivered continuously from the walls, and where the central object is both the drain and the ignition source at the same time. And the lid is not sealed. The Fermi bubbles prove that energy from this region escapes into the galaxy at large. The X-ray echoes prove that photons from past outbursts are still propagating through the surrounding medium right now. The galactic center is not a closed system. It is a system that leaks. And what it leaks has consequences that extend for thousands of light years in every direction. None of this was fully visible before. Pieces of it were known. The S-stars were tracked from the ground. The mini-spiral was mapped in radio. The Fermi bubbles were discovered in gamma rays. The X-ray echoes were seen by Chandra. But each piece lived in its own observational silo, studied by its own community, published in its own set of journals. What Webb has begun to do by providing a continuous, high-sensitivity, dust-penetrating infrared view that captures the entire inner region in a single field is connect the pieces. The flickering is connected to the streamers. The streamers are connected to the circumnuclear disk. The disk is connected to the central molecular zone. The central molecular zone carries the echoes of past outbursts. The outbursts drove the Fermi Bubbles, and all of it is organized around a single 4 million solar mass object that has never been still. That is the neighborhood. That is what surrounds the heart of the Milky Way. It is not a quiet place with a black hole in it. It is a dynamic, multi-layered, continuously fed, intermittently erupting environment that operates on every timescale from seconds to millions of years. And we orbit it. Every star you see in the night sky orbits it. The sun orbits it. You orbit it. The question that remains, the question that everything has been building toward, is not what Webb saw. We have covered what Webb saw. The question is what it means to know this. What changes, not in the data, but in you, when the center of your galaxy turns out to be not a pin on a map, but a permanent, unfinished process, closer than you thought and stranger than you wanted. There is an assumption buried so deep in how we think about scientific discovery that most people never examine it. The assumption is that seeing something more clearly makes it less frightening. That knowledge tames. That a thing you can name and measure and photograph becomes, by virtue of having been named and measured and photographed, smaller, less threatening, more contained. You shine a light into the dark corner, and the shape that scared you turns out to be a coat on a hook. The fear was ignorance. The cure was information. That model works extraordinarily well in most of science. It worked for disease, once we understood germs. It worked for lightning, once we understood atmospheric electricity. It worked for eclipses, once we understood orbital mechanics. The pattern is ancient and deeply comforting. You look closely, you understand, and the terror dissolves into comprehension. Sagittarius A star broke the pattern. Every major observational advance in galactic center science over the past 30 years has been an act of looking more closely. The stellar orbit campaigns looked more closely and found the mass. The Event Horizon Telescope looked more closely and produced the image. James Webb looked more closely and found the flickering, the flares, the continuous restless activity, the crowded neighborhood. The evidence of past outbursts written in X-ray echoes across the central molecular clouds. Each step brought more data, more resolution, more clarity. And at no step along that progression did the galactic center become simpler. At no step did the picture settle into something you could fold up and put in a drawer. At every step, the thing we were looking at turned out to have more structure, more activity, and more unresolved behavior than the previous step had shown. The coat on the hook, when you got close enough to really see it, was not a coat. This is the specific sense in which James Webb has made Sagittarius A star more disturbing than ever. Not because it found something apocalyptic, not because the black hole is doing something new or dangerous or aimed at us. It is not. Not because the data contains a threat. The data contains physics. The disturbance is that clarity did not produce closure. It produced the opposite. The better we see the center of the galaxy, the less finished it looks, and the less finished it looks, the harder it becomes to maintain the comfortable fiction that the heart of the Milky Way is a solved problem, filed away, no longer requiring our emotional attention. Let me try to articulate why that matters, because it is easy to wave this away as a philosophical nicety rather than a genuine shift in understanding. It matters because of what Sagittarius A star is structurally. It is not an object at the edge of the galaxy. It is not a phenomenon in some distant corner of the universe that we can choose to think about or not. It is the center, the literal gravitational center of the system we live in. Every star in the Milky Way, including the one that keeps us alive, orbits this thing. The Sun has been going around it for roughly 20 orbits since the solar system formed. The orbit is so vast that we cannot feel it. The timescale is so long that no human civilization has ever lasted for even a meaningful fraction of one lap. But the orbit is real. It is measured. It is happening right now. You are, at this moment, moving at roughly 220 kilometers per second around Sagittarius A star. You do not notice because everything around you is moving at the same speed in the same direction. But the motion is there. The gravitational tether is there. You are connected to this object in the most fundamental way. A mass can be connected to another mass through gravity, through orbital mechanics, through the large-scale structure of the galaxy that contains you. And the thing at the other end of that tether is not resting. There is a concept in the philosophy of science that is useful here, though I want to use it carefully. It is the concept of the unobserved center. For most of human history, the center of the Milky Way was literally unobserved. We could not see it. The dust was too thick. The instruments were too weak. The center existed, gravitationally, as a fact of orbital mechanics, but it had no visual presence, no sensory reality in human experience. It was an inference, a mathematical necessity, a place on a map that no one had actually visited, even with photons. When you cannot see the center of a system, you tend to imagine it as simple. This is a deeply human tendency. The unknown gets simplified, the hidden gets smoothed. When medieval cartographers reached the edge of their knowledge, they drew sea monsters and wrote, "Here be dragons," but the drawings were always simpler than reality. A dragon is a single creature. What actually waited in those unmapped regions was an entire ecosystem of complexity that no single drawing could capture. The center of the Milky Way received the same treatment. We could not see it, so we imagined it as a point, a mass, a number. 4 million solar masses, 26,000 light-years away. Clean, contained, abstract. Webb has made abstraction much harder to sustain. Consider what you now know as a result of everything described so far. The center of your galaxy contains a supermassive black hole that flickers continuously, flares unpredictably, and has no detectable resting state. Around it orbit stars moving at a measurable fraction of the speed of light, stars that should not have been able to form where they are and must have been delivered there by violent dynamical processes. Tangled in with those stars are strange, dusty objects that appear to be the remnants of stellar mergers, slowly being peeled apart by tidal forces as they drift through the black hole's gravitational influence. Feeding the whole region is a network of ionized gas streamers, drawing material inward from a thick molecular ring, itself the inner edge of a vastly larger complex of gas and dust that stretches across hundreds of light-years. That complex carries X-ray echoes of outbursts from the black hole that occurred as recently as a few hundred years ago, outbursts in which the black hole was temporarily millions of times more luminous than it is today. And extending above and below the galactic plane, like the exhaust of an engine that has been firing intermittently for millions of years, are the Fermi Bubbles, two colossal lobes of high-energy emission that reach 25,000 light-years into the galactic halo. None of that is new, in the sense that Webb invented it from nothing. The S stars were tracked from the ground. The G objects were identified years ago. The mini-spiral was mapped in radio decades ago. The Fermi Bubbles were discovered in 2010. The X-ray echoes were seen by Chandra. What Webb has done is not replace these observations. It has connected them. By providing the first continuous, high-sensitivity, infrared time series of the innermost region, Webb has made it possible to see the galactic center not as a collection of separate phenomena, but as a single, integrated system. A system in which the event horizon flickering and the century-scale outbursts and the million-year scale bubble inflation are all expressions of the same underlying engine operating at different amplitudes. That integration is what changes the mental picture. When the pieces were separate, you could hold them individually without feeling their combined weight. One piece was a flare, Another was a strange star. Another was a bubble in the gamma-ray sky. Each could be filed in its own folder. Once you see them as parts of a single active system, the filing does not work anymore. The center of the galaxy is not a fact. It is a process, and processes, unlike facts, do not have a final state. They are ongoing, they are unfinished. They will still be happening after everyone who reads this sentence is gone. I want to be very precise about the nature of the unease, because precision is the whole point. The unease is not that Sagittarius A star is going to do something harmful to Earth. It is not. The distance is too great. The energy of even a major outburst, spread over a sphere 26,000 light-years in radius, is diluted to insignificance by the time it reaches us. If Sagittarius A star went through another episode like the one that produced the X-ray echoes a few centuries ago, we would not notice it with our eyes. We would detect it with our telescopes. We might see the molecular clouds near the center brighten in X-rays. We would publish papers, but life on Earth would continue without interruption. There is no plausible scenario in which the galactic center threatens this planet. The unease is not physical, it is conceptual. It is the realization that the gravitational anchor of the system you live in is not an anchor in the way you imagined. Anchors are stable. Anchors sit at the bottom of a chain and do not move. What sits at the bottom of our gravitational chain is a thing that has never been observed at rest, a thing that flares without warning, a thing that has driven galaxy-scale outflows in the past and whose current quiet state may be temporary. The anchor is not broken. It is doing exactly what physics requires it to do. But it is not calm. It is not settled. It is not something you would describe, if you saw it up close, as reassuring. There is a deep human desire for the center of things to be stable. We build our cities around central squares. We organize our governments around central authorities. We build our solar system model around a central star and our galactic model around a central mass. The word center carries a connotation of fixedness, of reliability, of something you can orient yourself by, precisely because it does not change. When you learn that the center of the Milky Way is not fixed in its behavior, something shifts in how the whole system feels, not in how it works, in how it feels. The physics has not changed. Your emotional relationship to the structure you live inside has changed, and that shift, however subtle, is real. Webb has accelerated that shift more than any previous instrument, because Webb provided the one thing the mental picture could not survive: continuity. Before Webb, every observation of Sagittarius A star was a snapshot, a moment, a frozen frame. You could always tell yourself that the variability was an exception, that between the snapshots the object was quiet, that the flares were rare events against a background of stillness. Webb took that escape route away. By watching for hours at a time, it showed that there is no background of stillness. The flickering is the background. The flares are on top of it. And underneath the flickering, there may be even deeper layers of variability on longer timescales that we have not yet had the patience to resolve. Every layer we peel back reveals more motion, not less. This is, I think, the deepest reason why the Webb result feels disturbing in a way that is hard to put into ordinary language. It is not that the data is scary, it is that the data resists completion. In most areas of science, you make progress by moving from uncertainty towards certainty. You start with a question, you gather data, you converge on an answer, and eventually the question is resolved. The thing is understood. You move on. Sagittarius A star has been resisting that trajectory for 30 years. Every new instrument that looks at it produces not a closing of the question, but an opening of new questions. The mass measurement did not close it. The image did not close it. The Webb time series did not close it. Each advance has revealed that the object is more dynamic, more structured, and more behaviorally complex than the previous generation of observations had shown. The trend line, if you plot understanding against time, is not converging, it is diverging. We know more than we did, and what we know is that the center is stranger than we thought. There is a word for this situation in epistemology, the study of knowledge. It is called expanding ignorance. It describes cases where learning more about a subject increases, rather than decreases, the number of open questions. It is not a failure of science, it is a feature of genuinely complex systems. The more you learn about the ocean, the more you realize you do not understand about the ocean. The more you learn about the human brain, the more you realize you do not understand about the human brain. And now, the more we learn about the galactic center, the more we realize we do not understand about the galactic center. That is what makes the Webb result different from a simple update to a textbook number. It is not new information that slots into an existing framework. It is information that strains the framework. The framework said that Sagittarius A star is a mass at a location. The information says that Sagittarius A star is a continuous, unpredictable, multi-timescale process embedded in a dynamic environment that has been reshaping the inner galaxy for millions of years and shows no sign of settling into a steady state. Those two descriptions are not compatible. The framework will have to change. I want to end by talking about distance, because distance is the last piece of the comfortable fiction, and it is the piece that Webb has damaged most quietly. 26,000 light-years sounds like a lot. It is a lot. It is further than any human has traveled or will travel in many lifetimes. In the ordinary sense of the word distance, it provides safety. You are far from the galactic center. Whatever happens there happens far away. The flares do not reach you. The outbursts do not touch you. The flickering is not your concern. But distance in a galaxy is not the same as distance on a planet. On a planet, distance separates you from things. In a galaxy, distance connects you to the center through gravity. The orbit you are on right now, the orbit of the Sun around Sagittarius A star, is a physical connection. It is not a metaphor. It is not a loose analogy. It is a gravitational bond, as real as the bond between the Earth and the Sun. The center of the galaxy is not somewhere else. It is the somewhere that defines your somewhere. Your position in the Milky Way is described in every astronomical coordinate system relative to the galactic center. When you give your address in the galaxy, the center is the origin of the coordinate system. It is the 0 point. Everything else, including you, is defined by its displacement from it. That is a strange kind of distance. You are 26,000 light-years from a thing that you are also, in the most structural sense possible, organized around. You are far from it and defined by it at the same time. And when that thing turns out to be more active, more dynamic, and more unresolved than you assumed, the distance does not fully insulate you from the implications, not physically. Physically, you are safe. But structurally, organizationally, the thing you are orbiting has turned out to be less like a monument and more like a weather system. And you are inside its sphere of influence, whether you think about it or not. This is the hidden centrality that I want to leave you with. Not a threat, not a warning, a reorientation. For most of the history of astronomy, the galactic center was the one part of the Milky Way we could not see. It was behind the dust. It was beyond the instruments. It was an inference, a gravitational ghost, a mass without a face. And during all that time, it was easy, natural even, to treat it as settled, to treat it as the boring part of the galaxy. The part where nothing interesting was happening, the dead center, the still point, the anchor. Webb has shown that none of those words apply. The center is not dead. It is not still. It is not boring. It is not an anchor in any sense that the word anchor was meant to convey. It is an active, variable, multi-layered, continuously fed, intermittently erupting engine that operates at the gravitational pivot of a galaxy containing hundreds of billions of stars. It has been doing this for millions of years at minimum. It was doing this before the solar system formed. It will be doing this long after the solar system is gone. And every attempt to look at it more carefully has revealed not less activity, but more. That is what James Webb has made more disturbing than ever. Not the black hole itself, not the mass, not the distance, the realization that clarity does not domesticate the galactic center. The better you see it, the more alive it looks. The more alive it looks, the harder it becomes to pretend it is a dead point on a map. And the harder it becomes to pretend it is a dead point on a map, the more you have to sit with the fact that the center of the system you live in, the thing everything you have ever seen in the night sky is orbiting, is not finished. It is not resolved. It is not understood. It is not resting. It is not even stable in any intuitive sense of the word. It is just there, flickering, flaring, doing whatever it does in the infrared dark behind the dust, unreachable, unmistakable, and more real than it has ever been. 26,000 light-years away, and at the center of everything. The most disturbing thing about the heart of the Milky Way is not what it is. We have known what it is for decades. The most disturbing thing is that the closer we look, the less finished it appears. And we have just begun to look.